Hello everyone, welcome back to mmWave. Today we're going to explain three important mmWave components which mmWave offers. 282 series fixed polarizer, 283 series adjustable polarizer, and 281 series Orthomode transducers or OMTs. These components are widely used in satellite communication, radar systems, radio, astronomy, and high-frequency RF applications, where polarization control is critical. Many engineers understand frequency and gain, but polarization is equally important because it determines how electromagnetic waves are transmitted and received. So today we will answer what is polarizer, what is the difference between RHCP and LHCP, when should you use a fixed polarizer or adjustable polarizer, and how does an OMT create separate RHCP and LHCP channels, as well as how do we test axial ratio. Before talking about polarizers, let's first understand the polarization. An electromagnetic wave consists of electric and magnetic fields. The direction in which the electric field rotates is called polarization. There are three common types: linear polarization, right-hand circular polarization, which is RHCP, and left-hand circular polarization, which is LHCP. In linear polarization, the electric field stays in one plane. For example, vertical polarization and horizontal polarization, the electric field does not rotate. In circular polarization, the electric field rotates as the wave travels. If the electric field rotates clockwise, when viewed in the direction of propagation, it is called right-hand circular polarization or RHCP. If it rotates counterclockwise, it's called left-hand circular polarization or LHCP. So now, what exactly does a polarizer do? A polarizer is a passive RF component that converts one polarization state into another. For example, a waveguide antenna may generate linear polarization. A polarizer can convert linear polarization to circular or circular polarization to linear polarization. Let's imagine a satellite communication antenna. The feed antenna produces vertical polarization. However, the satellite link requires circular polarization because circular polarization is less affected by satellite rotation and atmospheric effects. So we add a polarizer. The antenna now transmits circular polarization after we add the polarizer. Let's start with the simplest type, the fixed polarizer. A fixed polarizer creates a fixed polarization state. For example, a fixed polarizer can be designed so one orientation produces RHCP and the opposite orientation produces LHCP. The physical orientation of the polarizer determines the polarization direction. For example, polarizer installed in one direction will put out RHCP output. If you rotate the polarizer 180 degrees, then the output will be LHCP. So the important point is the polarizer itself does not electronically switch polarization. You physically rotate or orient the component. Suppose we have a satellite ground antenna. The customer requires to transmit RHCP signal. We install the fixed polarizer just before the antenna in the RHCP orientation. Now the antenna will transmit RHCP while it receives LHCP. If we disconnect the polarizer and we orient in 180 degrees and connect it again in the assembly, then the antenna will receive RHCP and it will transmit LHCP signal. This is ideal when polarization requirement never changes and lowest cost is required. What happens if the user needs to change the polarization but disconnecting and orienting the polarizer is not possible? Then we use an adjustable polarizer. An adjustable polarizer includes a mechanical adjustment knob. Simply rotate the knob until it aligns with the desired marking such as linear, RHCP or LHCP. and the polarizer changes the output to the selected polarization. This allows you to switch between the polarization states without orienting the component. Now let us discuss Orthomode transducer or OMT. An OMT is a waveguide component that separates two orthogonal polarization signals. Normally, a waveguide supports vertical polarization and horizontal polarization. OMT has three ports. The first is the antenna port, which is a circular waveguide that connects to the antenna or feed. The other two are rectangular waveguide ports, one for vertical polarization and the other for the horizontal polarization. The OMT separates two orthogonal linear polarization signals into these two independent ports. Now comes the interesting part. What happens when we connect a polarizer to an OMT's antenna port? When a circular polarizer is connected to the antenna port of the OMT, these two rectangular ports become RHCP and LHCP ports, allowing simultaneous transmission or reception of both circular polarizations. Now that we understand a polarizer and an OMT transducer or OMT, let's look at where they are actually used in real-world RF and mmWave systems. One of the most common applications is satellite communication. Why? Because many satellites use both right-hand circular polarization and left-hand circular polarization to carry different communication channels. Using opposite circular polarizations allows the same frequency band to be reused while minimizing interference between channels, effectively increasing system capacity. So, how does a ground station receive both of these signals? The antenna first receives the incoming RF signal. A circular polarizer is connected to the antenna feed, and behind it is an OMT. As we already know now, the OMT has three ports. One is circular waveguide port, called antenna port, and two rectangular waveguide ports, vertical, horizontal. On its own, the OMT separates vertical and horizontal linear polarizations. However, when a circular polarizer is connected to the circular antenna port, those two rectangular ports effectively become RHCP and LHCP ports. This means one receiver can process the RHCP signal while another receiver simultaneously processes the LHCP signal, all using the same antenna. Now let's answer one of the most common questions about OMTs. If an OMT has only vertical and horizontal ports, how do these ports become RHCP and LHCP ports when we connect a polarizer? Let's say we want to transmit RHCP signal. The transmitter sends two orthogonal linear components through OMT, vertical component and horizontal component. The OMT combines these two components at its circular waveguide port. The signal then enters the polarizer. The polarizer creates the required phase relationship between the two components. A circularly polarized wave requires two equal electric field components with a 90-degree phase difference. When the phase relationship is correct, vertical component plus horizontal component with one phase rotation creates RHCP. If the phase rotation is reversed, it creates LHCP. Now let's look at the received direction. When the RHCP signal enters the polarizer converts RHCP to linear polarization components. The polarizer does not create RHCP or LHCP from an incoming circular signal. Instead, it converts the circularly polarized wave into two orthogonal linear components. At the output of the polarizer, we now have vertical electric field component and horizontal electric field component with the required phase relationship. The signal then enters the circular waveguide port of the OMT. The OMT's job is to separate these two orthogonal linear components. It separates vertical component to vertical rectangular port and horizontal component to horizontal rectangular port. So the OMT is not directly splitting RHCP into one port and LHCP into another. It is separating the two linear components that make up the circular polarized wave. Now the question is, if the OMT ports are vertical and horizontal, why are they sometimes labeled as RHCP and LHCP? The reason is that the complete assembly is considered together polarizer plus OMT. The rectangular OMT ports are physically linear polarization ports. However, after connecting the polarizer, the phase relationship between the vertical and horizontal components is controlled by the polarizer design. Therefore, depending on the polarizer orientation, one OMT port corresponds to the RHCP channel, the other OMT port corresponds to the LHCP channel. The exact port assignment depends on the polarizer design and mechanical orientation. A simple way to visualize this is circular polarization is created from the two building blocks, vertical electric field and horizontal electric field. The OMT separates these two components. The polarizer controls how these components combine. When the phase relationship is in one direction, vertical plus horizontal with 90-degree phase shift converts to RHCP. When the phase relationship is reversed, vertical plus horizontal with opposite 90-degree phase shift converts to LHCP. In our upcoming videos, we will continue exploring the world of waveguides, antennas, filters, frequency converters, and other technologies that make modern communication systems possible. Thank you for watching and see you in the next RF journey.